Okay, so now we're finally ready to just analyze this code. So let's do it. And we literally just have to, trace through it. It's 5 lines long. So it'll actually give us like a nice practice at like using, like our new tensor product notation and stuff. You might enjoy like doing it yourself in like maybe in a more old-fashioned way if you kind of pretend that like maybe M is 2 and like R is like some, little unitary and like draw some of those like cube diagrams. But we'll try to do it with our nice fancy notation now. So, all right, after line 1, what is the state? So there are m plus 1 qubits here. And after line 1, well, like before line 1, the state was this. It was like ket start. Okay, and this was like the state of like A1 through AM. But after line 1, we make a new qubit called D. But like, that's literally what this means. Okay, the new state is this new vector, and it's this tensor product. D is in the state 0. Okay. So what about after line 2? Okay, so in line 2, we only do an operation on D. So it's still like actually like Dave, the owner of D, could have done like lines 1 and 2 in Dave's own office. So like we really only have to understand like how ket 0 changes when we do add and diff on it. And then it'll still be like unentangled. So like after line 2, all I'm saying is like the new state will be start tensor product, whatever you get by doing add and diff to ket 0, which I know you remember is just this, ket 0 plus ket 1. Oh, I should also add that like this line makes us unnormalized by like a factor of square root 1/2, but this line makes us unnormalized the other way by like square root 2, so they cancel out. So it's a small aside, because we're doing the same number of add and diffs as average and divs, we end up normalized at the end here. Actually, we end up normalized here. And that's convenient. Okay, so we're like a little bit unnormalized here, but we're going to fix it later. Okay, so now finally we do this big line 3. Actually, let me multiply this out. This is the same as like start tensor 0 plus start tensor 1. Okay, and now after line 3. Okay, so all this stuff together is like one giant qubit manipulation operation operating on n plus 1 qubits. And we know those are linear, which means that like you can just apply the operation separately to each of these pieces. So we can just say to ourselves, all right, in the stuff where this is the D part. This is like the A1 through AM part. Here D is 0. So when D is 0, like we don't do anything. We don't do any rotation. So like after line 3, we get the first part is ket start, tensor 0 still. And then here, like D is 1, so we do a rotation. So like this is R applied to ket start, tensor with 1. Okay, so as I said, you kind of get into a state where you're like in this branch, or this piece of the state where D is 0, like you didn't rotate start, and in this piece where D is 1, you did rotate start. And now we're going to combine them. So after line 4, okay, we're doing average and div on D. And if you remember the slogan of that, like you say to yourself, oh, on the part where D is 0, you get the average of the two amplitudes. And on the part where D is 1, you get the deviation of the two amplitudes. And I'll let you think about this a little bit, but like it really works even when these are not just the numbers, but these are vectors, because you kind of just do the average amplitude-wise or component-wise, and the deviation amplitude-wise or component-wise. So if you look at the notes, I draw a little diagram to help explain that. But let me just say for now, it's a little exercise. You can check that you get to what I'll call ket average tensor 0 plus ket div tensor 0, where this ket average and ket div are like the average and deviation of ket start and r ket start. So where average is start plus r start over 2, and like div, that's like vector addition. It's like start minus r start over 2. So now I'm going to draw a picture. We have some nice markers here. Okay, so let's say this board is P, the two-dimensional plane of rotation. And start, this is like maybe the origin, which is in P. And start is some like unit vector, like this. Okay? And let's also depict R applied to start. And R applied to start, well, by definition, R applied to start like rotates start by angle theta within this plane. So we get another unit vector, R applied to start, also in this plane. Okay, and this angle is theta. Okay, now what is ket average? Well, it's just the average of these two vectors. So the vector average. So, I mean, these are high dimensional vectors, but they're both in this plane P, and their average is, I think, like right here. So it's not a unit vector. It's like shorter than unit. But it's like, this is like their midpoint. This is theta over 2. This is theta over 2. And this is ket average. And then what is ket div? Well, it's always like the amount by which the first vector differs from the average. So, or it's like start minus r start. Start minus r start is the vector like this, but half of that. So, okay, what I'm saying is like this is div. Okay. And, okay, so this is a right angle. And one thing I can say is average and div are also in this plane P, because they're just averages and deviations of these two things in plane P. Also, like, this is length 1, and this is angle theta over 2. So this length of div is sine theta over 2. That's how sine works. Okay. So, this is where we got to after line 4. This should have said 1. Sorry about that. This is D. This is D. Good. So now, if you remember, like our some stuff about our fancy notation that we saw in like a couple lectures ago. If you're in some, big entangled state, and you extract just one of the qubits, which is what we're doing here in line 5, we're extracting just the D part, then it's real good to write your state in this sort of form where it's like ket 0 for D tensor something plus ket 1 for D tensor something. And I hope you remember in line 5, when we do extract D, like what is the probability that you see outcome D to be 0? It's basically like this thing squared. Well, this thing's length squared. That's something we saw, I don't know, maybe 2 lectures ago. So it's the dot product of average with itself, or like the length of this thing squared. Which actually we're not going to really care about that much, because what we're really trying to show is this. But anyway, like the length of average squared is cosine of theta over 2. So I can tell you this is cosine theta over 2 squared. Moreover, and if this occurs, the new state of A1 through AM is average. Well, normalized. This is not a length 1 vector, so you can normalize it if you want. Okay. Well, that's actually not the outcome we care about, but like I think you'll see we're in good shape now, because like the probability that you get outcome d equals 1 is, well, it's the length squared of div, which we just computed as sine theta over 2 squared. Yeah, so this is sine theta over 2 squared. Okay, and that's exactly what we wanted here. And if this occurs, the new state of the A's is this div vector. Again, also normalized. Okay, and that double checks that this occurs. Because there are 2 possibilities. This ket nu, the final state of the qubits, it's either this average vector or this deviation vector. But either way, it's still in P. So just as we desired. Okay, so that's kind of the end of this like Hadamard sort of self-test that you can use to sort of estimate or do like one round of estimation of like how much a unitary R rotates a given starting state. Yep. Well, you could, okay, given, I'm not sure, exactly sure what you mean. So like given start, you can apply R to it, and that'll like rotate start by some like amount theta that you don't know, and you'll have like a new vector R start. So you'll be in the same position where you're like, well, now my states, or qubits A1 through AM are, I know they're got a state which is a vector in P, but I didn't really learn anything. I just moved the starting state. So I need to do something that helps me, I'm trying to do something that helps me learn how much R rotates vectors here. So this Hadamard test has like the dual feature that like this signal gives you a bit of information about how much start rotates when you apply R. And the good news is it like doesn't ruin the states at all, or it like mostly doesn't ruin them. It changes them a little bit, but like it still leaves you with a state that's in this plane P. So you're eligible to do this like again. Don't know if that answers your question. I mean, the thing is like you could say like great, like I'll just throw these qubits in the trash, and maybe I'll get like a new copy of the original start and measure it again. But this you cannot do because, as I was trying to explain before, we don't see it yet, but like we're going to be in a situation where we don't have the ability to like recreate start. So whatever like starting state we have, we kind of have to like save it or like save something related to it. Okay. Now I will, in the last 3 minutes, do something very boring, which is I'll just write on the board like a giant summary of rotation estimation, so that we can forget it. So that when we come back from Thanksgiving and we're like, what happened? There's so many details. There's rotations and intervals and mediums and Hadamard tests and so many things. We'll just like try to remember the interface to the final form of rotation estimation. Okay, so here it is. Okay, so input. there's going to be n, the number of digits of precision you want. And you're going to want code for a unitary R that you really care about on, some qubits, A1 through AM. And also code for R to the 10, R repeated 100 times, all the way up to R repeated 10 to the n times. As I said, when we do factoring, we're going to have some special purpose code that can miraculously do this in n instructions rather than 10 to the n instructions. And we're also going to assume that you have A1 through AN are initialized to a state get start in one of R's 2D planes of rotation. And the goal of the algorithm is to figure out how much R is rotating in this particular plane. But I'll just say that when I say about the output. Okay, that's the input. And then I want to remember something about the form of the algorithm. This is what we talked about at the first 20 minutes of class when I said you can reorganize the code so it makes all its qubits, then does all its unitaries, then does all its measurements, then processes the result. So the form of the algorithm is that it makes C times n new qubits D1 through dCn, where C is some big constant 100,000. Then it does all its unitaries. So it uses the code for R and for R to the 10 and R to the 10 to the n, C times each. Where C is a constant. So again, if you have this code is pretty efficient, and this code is pretty efficient, and this code is pretty efficient, then you're only using each of them a constant number of times, and there's only n of them. So think of n as 1,000. So the total work is going to be C times n times the complexity of each of these things. So that's fine. Okay, it does all its unitaries. Then it extracts all the d's, giving some classical data, D1 through dCn. And then finally, there's a simple classical algorithm that processes the d's and giving the final estimate theta hat. Oh, I'm out of time. Well, the last thing I'll say is, and then that's it, the output is with overwhelming probability theta hat equals theta, the amount by which R rotates in P, to n digits of precision. Okay, that's it. If you really want to see some fine print about the glitch, you can read that in the notes.